method will take as argument, well, first self to refer to the object, but then, as you might guess, it will take the experience, right? Because first this method step stores experiences. However, we're not going to directly input here experience. We're going to decompose the experience into its different elements: state, action, reward, next state, and done. Alright, so that's going to be the arguments of the step method. Then let's add a colon, and there we go. Let's implement it. So the first thing it's going to do is to store the experience in the replay memory. And therefore, since we already created our memory object with self.memory as an instance of the replay memory class, well, we're going to call our self.memory object. So I'm taking it here, and then I'm pasting it right here. And then remember, in the replay memory class, we also implemented the push method that stores an experience in the replay memory, and therefore, of course, we're going to add a dot here to call the push method from this self.memory object. Then we add some first parentheses because it's a method, a function, but then we're going to add another pair of parentheses because we have the experience decomposed like that. So in fact, in order to enter the experience here, well, we're going to enter the whole tuple of the state, action, reward, next state, and done. So I'm taking this, and just inside, I'm pasting it. All right? Perfect. Now, next step. So remember that this step method does two things. First, it stores the experience, so that's what we've just done. But then also, it decides when to learn from the experience. And so basically, what we need to do now is increment the time step counter, which is one of our object variables here, self.tstep. We're going to increment this time step counter and reset it every 4 steps so that we can learn every 4 steps. All right? And we will learn with another method that we will call the learn method, and that we will implement later on in this agent class. So what we're going to do here is take this self.tstep object variable, and then just below, we're going to paste it because we're going to update it by first incrementing it and then resetting it every 4 steps. So first, let's start by incrementing it, meaning adding 1 to it. And the way we're going to do this is very simply paste it again and then add +1. Alright, so that's the increment. We increment the time step counter. But now we also want to reset it every 4 steps, and we're going to do that in the same row. And well, the way to do that is to use modulo. I don't know if you know this. If I put some parentheses here and then add a percentage and then 4, well, all this exactly means the rest of the Euclidean division of self.tstep plus 1 by 4. Meaning, if self.tstep plus 1 is divisible by 4, then all this will be equal to 0, because the rest of the division would be 0. And therefore, that checks if we are every 4 steps. Alright? So, new step done, good. And now, time for the last part of this step method, the learning, which would happen only if we have reached 4 steps, every 4 steps. And therefore, what we need to do now is an if condition that checks if we are every 4 steps. And the way we're going to do this is, of course, with if, and then self.tstep. And now, since self.tstep is actually equal to the rest of this division by 4, then the way to check if we have reached a new 4 steps is just to do this if self.tstep is equal to 0. Alright? And so, if that's the case, then what are we going to do? Well, we're going to learn, because we want to learn every 4 steps. But then, remember that when we learn, we don't learn on one observation only. We actually learn on a mini batch of observations. That's why we created the mini batch variable before, which we initialized to 100. And therefore, what we must do first before learning in the step method is to check that the number of experiences in the memory is already larger than this mini batch size of 100. And therefore, we're going to continue here with another if condition, which will check if the length of our self.memory object, but more specifically, it's going to be an attribute of that memory. So first, let's paste self.memory, and then let's get a quick refresher of what we did in the replay memory class. I'll show you that it has a specific attribute, which is actually the memory, and it's actually not to be confused with the self.memory instance of that replay memory class that we just created here. So basically, simply put, this is the instance of the replay memory class, and then in order to call the memory attribute that we see here, well, we just need to add .memory here. Okay, so this is the object, the instance of the replay memory class, and this is the attribute of this self.memory object. Alright, I think it was important to clarify this, but there we go. So now we have the memory size of our memory, basically. And so, if that memory size is larger than the mini batch size, which we also created and initialized before right here of 100, well, in that case, we can learn. We can learn on 100 observations instead of just one observation. In AI and reinforcement learning, we always learn on a mini batch of observations as opposed to one observation. And so then let's add a colon here. And so if that's the case, well, what do? First, we're going to get our experiences. So I'm creating a new local variable here which will contain this mini batch of 100 experiences. And how am I going to get them? Well, I'm going to use, of course, another tool we created before, which is the sample method from the replay memory class. And so to do that, I have to take my self.memory object, the instance of the replay memory class, and then from this object, I'm going to call that sample method, right? Which will sample 100 experiences from the memory. And it will find them because we check that the size of the memory is larger than the mini batch size of 100. So there we go. Let's enter 100 here, of course. And so now we have our experiences, and therefore the last step is to learn from those experiences. And of course, we're not going to implement the learning algorithm right now. We'll do that in a separate method. But since we will call that method learn, what we can do now is actually to call this method learn, which will be implemented in 2 tutorials, and which will take as input, of course, our sampled experiences, but then another one, which is the discount factor gamma, which remember we called discount factor, or maybe you called it gamma, when we initialized the hyperparameter. And that, what we did here to call the learn method even before defining it, is totally fine, as long as, of course, we define it after in this agent class. Alright? So there we go. We're done with this new step method. Now we can move on to the next method, which will be the act method, which will be, of course, the method that will select an action based on a given state in the environment. I can't wait to implement this new method with you in the next tutorial, and until then, enjoy AI. Hello my friends, and here we go with the implementation of a new method of our agent class, which will be the act method that will select an action based on a given state and a certain epsilon value for an epsilon greedy action selection policy. So here we go. Let's start by defining this new act method, which will take as arguments, well, first self for the object, but then, since it will select an action based on a given state, well, it will take, of course, the state. And then also, since we're going to do an epsilon greedy action selection policy, well, it's going to take, of course, epsilon as the last argument. And we're going to give it a default value, which will be 0 point to make it a float. And here we go. Now let's define that act method. Alright, so first what we have to do is start from the state, because right now at this point the state is a NumPy array and we need to make sure it is a torch tensor so that we can work with the neural networks later on. So what we're going to do is call this function we know already from the torch library, which is of course the from NumPy function, right? And which will take the state as input, so far a NumPy array, but which will be converted into a torch tensor. Then we're going to make sure to set the data type as a float. And then we're going to do something else that we haven't done before, but which is extremely important for any deep Q-learning, deep reinforcement learning that you're doing. We need to add here an extra dimension to our state vector. Right now, we have 8 dimensions of the state, corresponding to the coordinates of the spaceship, the velocity vector, and etc. But we need to add an extra dimension which will correspond to the batch, meaning that this extra dimension will say which batch this state belongs to. Alright, because we're going to work with mini batches. Instead of learning on 1 observation, we're going to learn on 100 observations. And so we need to know for each state in which batch it belongs. Alright, and so that's exactly what we're about to do now. And the way we're going to do this is with a dot and then adding unsqueeze, then parenthesis, and then in the parenthesis you're going to have to enter the index of which you want this dimension of the batch to be. And since we usually put the dimension of the batch at the beginning, before the other dimensions of the state, well, we're going to enter here 0. So that the first dimension of our new state vector, but now torch tensor, will be at the beginning. Okay? So then we're just going to add 2 parenthesis self.device, just to move it to the designated device, GPU or CPU. Perfect. And so, since all this actually updates the value of the state variable, well, we're going to add here state equals all this, so that now our state is updated to be a torch tensor set as a float with this extra dimension of the batch added and sent to the designated device. So that's perfect. Now, next step, well, because we're about to forward pass the state through the local queue network to get the action values, well, we're first going to set our local queue network to evaluation mode. And the way we're going to do that is by taking first our local queue network and then add a dot and then call the eval function. So where does this eval function come from? Well, that's because remember, local queue network was created as an instance of the network class, and remember the network class actually inherits from the, let's go back to part 2, it inherits from the module class by the NN module. And so we can use now the tool of the module class by the NN module, and one of these tools is of course the eval method to set our local queue network in evaluation mode. So let's go back here, there we go. Now thanks to this eval method we are in evaluation mode, and now we can forward path the state through our local queue network to get the action values. And how we're going to do that? Well, first we're going to make another check to make sure we're not in training mode but in inference mode, meaning that we're doing predictions. And so to do this we're going to add torch to call the torch library, and then from the torch library we're going to call the no_grad function, which will make sure that any gradient computation is disabled. Alright, then you're going to add a colon, and then just below, well, there we go, we're going to do something very exciting now. We're going to finally make the predictions from our local queue network to get the action values. And how we're going to do that? Well, first let's introduce a new variable, a new local variable, which we're going to call action values, which will be of course the actions predicted, with the queue values. And how we're going to get them? Well, we're going to call of course our local queue network while entering as input of course the state. And that's exactly how you forward pass the state to the output layer through our two fully connected layers to get the final action values. But in fact, you're getting the queue values corresponding to the actions. And then you'll see we'll use that epsilon greedy policy to select the final action. All right, so let's do this. Now, since we're done with the inference mode by, getting those action queue values prediction, well, we're going to go back into training mode. And the way we're going to do this is, of course, by first calling our local queue network. And then again, just like the eval function, since local queue network is an instance of our agent class and the agent class inherits from the module class by the NN module, well, we're going to use another tool of that NN module, which is this time the train method. And that's exactly what sets our local queue network back to training mode. So great, now we're back to training mode as opposed to inference mode, making predictions. And so now is the time to do that epsilon greedy action selection policy. And so how we're going to do that? Let me remind you how epsilon greedy action selection works. So basically we generate a random number, and then we're going to say if this random number is larger than epsilon, the epsilon we set here, then we're going to select the action with the highest Q value. And else, if our random number generated is lower than epsilon, then we're just going to select a random action. And so, since I just explained to you what is epsilon greedy action selection policy, well, try to press pause on the video and try to implement this if condition yourself to select that final action based on this epsilon greedy action selection policy. But now I'm going to do it with you. Here we go. So we're going to start with if, and then let's generate first this random number by calling first the random library, from which we're going to call this time the random function, right? We have first the library and then the function. And so we're going to check that if this random number generated is larger than epsilon, then what are we going to do? Well, we're going to do, of course, we're going to select the action with the highest Q value. And so, well, directly we can return that action with the highest Q value. And how we're going to do that? We're going to use a tool from NumPy, which is the argmax function, and which will allow us to do exactly what we want, meaning select that action that has the highest Q value based on the action values we already got here. Okay, so let's do this. We call NumPy first, and then from NumPy we call this argmax function, which will take as input, of course, our action values. But then, since this selection is a simple operation, we're going to send that to the CPU. And then, because the argmax function actually expects a NumPy format of data, well, we're just going to add here .data dot numpy with some parentheses. And there we go. That will exactly select this action with the highest Q value. All right, good. And now we're going to do the else, meaning if the random number generated is lower than epsilon, then what are we going to do? Well, we're going to just select a random action. And so the way to do this is very simple. We're going to return a random action by using the choice function by the random library. So here we go. I'm calling the random library first, from which I'm calling this choice function. And then the trick, to select a random action among our 4 actions, which remember are 0, 1, 2, or 3. Well, the trick to do that is just to use numpy and then this function from numpy called arrange. And then inside we just have to specify the action size, meaning 4. In other words, we're going to select a random index among 0, 1, 2, and 3, because 4 is excluded. Okay, so that will exactly select a random number between 0, 1, 2, and 3. Alright, so that's perfect, and we're done with this new act method that will select an action based on an epsilon greedy action selection policy. Perfect! So now we're gonna move on to the next step, implementing that new method, which will be the learn method finally, which will of course update the agent's Q values based on our sampled experiences. I can't wait to do that with you in the next tutorial, and until then, enjoy AI. Hello my friends and welcome to this new tutorial, a very exciting one because finally we're gonna implement that learn method of the agent class that will update the agent's Q values based on sampled experiences. So, it's quite a big method, so let's get started. We're gonna define this learn method, which will take, of course, as argument self for the object, then our sampled experiences, and then the discount factor gamma. Or if you want, you can call this gamma. All right, then colon, and here we go. So let's scroll down here to give some space. And the first thing we're going to do now is unpack our sampled experiences into their respective categories, meaning states, next states, actions, rewards, and dones. So here we go. We're going to create these new local variables here, which are going to be the states, the next states, the actions, the rewards, and dones. And according to you, what are they going to be equal to? Well, of course, our experiences, because our experiences are exactly the tuples of these elements. All right. So we're just basically now separating, unpacking the experiences into the different elements, states, next states, actions, rewards, and dones. Okay, good. Now next step. The next step now is to get the maximum predicted Q values for the next states from the target network. And why is that? That's because then, remember, we're going to compute the Q targets for the current states, which include those maximum predicted Q values in the formula. So let me show you. First, let's get these maximum predicted Q values for the next states, which we're going to call next Q targets. Okay. And how we're going to compute them? Well, of course, we're going to use our target Q network, right? As opposed to the local one. Remember, we created with the constructor method in it here, we created our target Q network as an instance of the network class. So what I'm going to do now is take this and just below, I'm going to paste it here, because the first thing we're going to do now is forward propagate the next state from our target Q network. All right, good. And now, what does this give us? Well, this gives us the action values of our target Q network propagating the next state. And therefore, now, since we want to take the maximum of those action values, well, we're going to use the max function to get that maximum. But before, we actually have to detach the action values in the tensor in order to then get the maximum of them. So the detach function actually detaches the resulting tensor from the computation graph, meaning that we won't be tracking gradients for this tensor during the backward propagation. And then in this max function, we have to input a 1 here because we need the maximum value along dimension 1, which corresponds indeed to the action dimension in the tensor. But then it's not over. We also need to add here a square bracket 0, because actually after getting max 1, we get two tensors, a tensor of maximum values and a tensor of indices corresponding to the actions for these maximum values. And therefore, we need to add this 0 in the square brackets here to select just the maximum Q values tensor. But then actually what we'll have to do next is to add a dot on squeeze of again index 1, because we'll need to add again the dimension of the batch, but this time we'll add it at position 1. Alright, and that gets us the maximum predicted Q values for the next states from the target network, not the local network. And now that we have that, the next Q target, well, we can compute the Q targets for our current state. And so let's call them Q targets, just like that. And it's going to be, of course, the reward plus the discount factor gamma multiplied by our next Q targets multiplied by 1 minus DONS. Alright, that's exactly the formula giving us the Q targets for the current state. Make sure to remember that formula. You will implement it many other times. Okay, awesome. So now, next step is to get the expected Q values from the local Q network this time. Okay, so this time we're going to forward propagate the state from our local Q network, as opposed to propagating the next state from our target Q network, as we just did. So let's do this. Let's call these new expected Q values Q expected. Okay, and then, as we just said, well, we're going to forward propagate the states from our local Q network, and therefore, let's just take it here. We're going to take our self.localQ network, copy it, paste it right below, and we're going to enter the state to indeed forward propagate the states to get the expected Q values from the local Q network. Okay, but then we're just going to add here gather, because we're going to gather all the respected Q values returned by our local Q network. And so how we're going to do this? We're just going to add 1 and then actions here in this gather function. Alright, so now that we have our Q targets and our expected Q values, well, finally we can get the loss, meaning we can compute the loss between the expected Q values and the target Q values. And therefore, that's exactly going to be our next step here. We're going to create a new local variable, which we're going to call, of course, loss, and which will be exactly that loss between the expected and the target Q values. And so, how are we going to compute that loss? Well, we're going to call our functional module, which we gave the shortcut f, from which we're going to call a new function, which is the MSC loss function, computing the mean squared error loss between actual values and predicted values, here respectively Q expected and Q targets. So here we go. Let's call this function MSC underscore loss, computing the mean squared error loss between, and that's exactly what we have to input here in the argument, between first Q expected and then of course Q targets. Perfect. So now we have the loss, and so now according to you, what are we going to do? Well, of course, we're going to back propagate this loss in order to update the model parameters to then update the new Q values, leading to a better action selection policy. Okay, so let's do this. That's going to be our next step here. But first, we're just going to initialize the optimizer by zeroing out the gradients of that optimizer. Basically, we're going to do a reset. And the way to do this is by, of course, taking another object we created in the constructor method, which is, of course, self.optimizer. So I'm taking it here, and then back below, I'm going to paste it right here. And well, to reset it, I'm going to call the 0_grad method. All right, because optimizer was created as an instance of the Adam optimizer class. Therefore, it contains this 0_grad method as a tool. Okay, good. And now, finally, time for backpropagation. We're going to backpropagate the loss that we just computed to compute the gradient of that loss with respect to the model parameters. So let's do this. It's super easy. We're going to take our loss that we just computed here, and then we're going to add a dot and then call the backward function. And that's it. That's all we need to do to backpropagate this loss. Okay? And that computes at the same time the gradient of the loss with respect to the model parameters. Okay, great. Now, next step. The next step is to now perform a single optimization step to update the parameters of the model. And so how are we going to do that? Well, we're going to, I think I still have it copied. We're going to take our self.optimizer, there we go, from which this time we're going to call the step method. And that is a method that exactly performs a single optimization step to update the model parameters. Okay, perfect. And now, final step. The final step is to update this time the target network's parameters with those of the local network, just like in deep Q learning. And so how are we going to do that? Well, unfortunately, we can't do everything of it now. So what we're going to do is we're going to call the last method of this agent class, which we're going to create in the next tutorial, that will exactly do this update. And we're going to call it soft update. the soft update method, which will take as arguments our self.local queue network as the first argument, then of course our self.target queue network, and then finally, can you guess? When we do the soft update, we always use the interpolation parameter, and that's exactly going to be our next and final argument here. Perfect, so I'll see you in the next tutorial to implement that soft update method, and until then, enjoy AI. Hello my friends, and here we go for the final method implementation of this agent class. We're going to define now the method that will softly update the target network's parameters, and we're going to call this method soft update. So here we go. What is going to take as parameters? Well, first self for the object, then it's going to take our local queue network, so we can call that local model. Then the target queue network, which we can call target model. I'm just taking different names here so that we don't confuse with our variables created before. And of course, it's going to take as the last argument the interpolation parameter. Perfect, here we go. So colon, and then let's implement the soft update method. So first, what it's going to do is loop through the parameters of the local queue network and the target queue network. And so we're going to start with a for loop here that will loop through first the target parameters. So I'm calling this target param to keep things simple. Then it's going to loop through also the local parameters, meaning the parameters of the local model. So I'm adding here another loop variable, which I'm going to call local param. And then the trick to get those parameters at the same time is to use the zip function, which will take as arguments, of course, well, the parameters of the target model and the parameters of the local model. And how we're going to get them? Well, first, we're going to take our target model, from which we're going to call a certain attribute, because remember, of course, target model is supposed to be here, our target queue network, which we created here, target queue network. And remember, since this is created as an instance of the network class, and since the network class inherits from the module class by the NN module, well, we can use this attribute parameters, which will give us the parameters of the model. All right, so let's go back down, and that's exactly how we're going to get those parameters. So after target model dot here, I'm just going to add parameters and then some parentheses. All right, perfect. Then we're going to do the same with our local queue network, our local model. So I'm going to add a comma here and then paste it, and then just replace target here by local. All right, perfect. So let's add some colon here for the for loop, and then here we go. Let's now implement what's going to happen for each target parameter and local parameter of our two queue networks. So actually now is the time to do the soft update. And so as a reminder, the soft update consists of, well, softly update the target model parameters using the weighted average of the local and target parameters. And so first here we're going to take our target parameters, target param, and then since we want to update them, the target parameters, well, we could do an update like this, but instead we're actually going to use the copy function to update the parameters of the target queue network. And so the trick to do this is just to add here dot data and then dot copy underscore, which is actually a function. So I'm adding some parentheses here, and inside the parentheses you're going to have how you want to update those target parameters. And well, the formula of the soft update of the target parameters is as such. First, you take your interpolation parameter, which you multiply by your local parameters, local param. But actually, again, here to get them precisely, you need to add dot data. So that's the first part of the formula. And then you're going to add, well, this time 1, which I'm writing as a float, minus, again, the interpolation parameter multiplied by the target parameters, target param. And again, to exactly get those parameters, you need to add dot data here. And there you go. Double congratulations, because not only we're done implementing the soft update method, but also we're done implementing the agent class. So congratulations. We did some good work here, and mostly we have everything we need, meaning all the tools to implement the training. Now, what I'm going to do is just summarize everything we've just done here in a few words. So I'm going to zoom out a bit so that we can see everything, with a good bird's eye view. There we go. I hope it's not too small. Let me know in the comments if it's too small, and I can always update this and improve this. But there we go. Now we have a good look at the whole code we just implemented together. And so let me just summarize it again. First, we created this agent class that defines the behavior of an agent that interacts with our space environment using a deep queue network. And while it's interacting with this environment, the agent maintains two queue networks. First, the local queue network and then the target queue network. The local queue network is the queue network that will select the actions, and the target queue network is the queue network that will calculate the target queue values that will be used in the training of the local queue network. So it's very important to understand both what they do separately, and also what's important to understand is how they interact with each other, meaning that this double queue network setup will stabilize the learning process that we implemented here. And at the same time, we have the soft update method that will update the target queue network parameters by blending them with those of the local queue network, with that formula we implemented here. And what's the purpose of that? Well, that's to prevent abrupt changes which could destabilize the training. And also, we implemented the ACT method that will help the agent choose an action based on its current understanding of the optimal policy. Those actions will be returned from the local queue network that will forward propagate the state to return the action values. And then following an epsilon greedy policy, it will return the final action. And that epsilon greedy strategy is used as an exploration mechanism. The fact that sometimes we can select random actions allows the agent to explore some more actions which could potentially lead to a better result at the end. And then finally, the learn method uses experiences that are sampled from the replay memory in order to update the local queue network's queue values towards the target queue values. Alright, and that's it. That's the bird's eye view of what we just implemented. Huge congratulations again. Now we're going to move on finally to the rest of this training implementation. We're first going to initialize the DQN agent, and then finally we will train it to accomplish a beautiful landing on the moon. I can't wait to implement those new steps with you, and until then, enjoy AI. Hello my friends, and welcome to this new tutorial. It's going to be a very simple one because it will just take one line of code to initialize the DQN agent, because indeed now that we're done building our agent class, we can finally create an instance of that class. By the way, I forgot to run this cell in the previous tutorial, so I'm doing it super quickly here. All good. We're good with our agent class, and so now we're gonna initialize the DQN agent by simply creating an instance of that class. So here we go. Let's insert a new code cell here, and we're gonna call our agent object very simply agent. Okay, and then this object will be created as an instance of the agent class. Make sure not to forget the capital A, which will take as input, of course, the state size, but then be careful not to input action size. That was the name of the argument in the agent class, but actually when we initialize our variables just a bit above, we called action size number actions, or maybe you called it action size if you're used to it, but maybe number action speaks better for itself. So we're gonna take that name here, the name of that variable we initialize while setting up the environment, and we're gonna paste it right here. And there we go. That's all we need to do to initialize the DQN agent. So now we can simply run that cell, and congratulations, you now have for real an artificial intelligence. All we've been doing before was just the architecture of it, modeling it, but now we really have it because we finally created the object. So that's super exciting. Now in the next tutorial, we will of course train it, because so far we only built an AI with a non-trained brain. And so we need to train that brain with the tools that we implemented here. By tools, I mean the step method, the act method, the learn method, of course, the soft update method. So we will use all these tools to train the brain of our AI. And that's exactly what we'll do in this new step, training the DQN agent. So I can't wait to do this with you. And until then, enjoy AI. Alright my friends, here we go. Let's start the training implementation. So we're going to add a new code cell here. And before we start this big for loop that will perform the training, of course, we need to initialize the training parameters. And which are they? First, it's going to be the number of episodes. which is actually the maximum number of episodes over which we want to train our agent, but you will see that it will already get some amazing performances before that maximum number, and so we'll initialize this number to 2000, okay? But you will see if we're getting the same results as when I tested it myself, well, we should get some good reward even from a couple hundred episodes. But I don't want to tell you more now. I want to keep you surprised at the end. So here we go. Let's proceed with the next training parameter. So the next training parameter is going to be the maximum number of time steps per episode, meaning that we don't want to let our AI try too hard. For example, if it keeps staying in the air, or if it stays too long in a certain stuck state of the environment, we don't want this to happen. So we're going to set a maximum number of time steps per episode. And to make things super clear here, so you can read the code easily, I'm going to name this variable, and this is just for educational purposes. I'm going to name it maximum number time steps per episode. Of course, feel free to choose a simpler variable name, but at least we will be able to read our code exactly like we would read our native language, okay? So maximum number time steps per episode, and we're going to initialize that to 1000. In any attempt on landing on the moon, there's going to be maximum 1000 time steps. Perfect. Then, next training hyperparameter to initialize, well, it's actually going to be a series of 4 corresponding to the same thing, which are the hyperparameters related to our epsilon greedy action selection policy. Because you might have wondered, what will be this epsilon value over which we want to compare this random number generated, to either select the action with the maximum Q value or select a random action for exploration. Well, here's how we're going to do it. We're going to start with an epsilon starting value. Again, I'm taking very simple variable names so that we all understand what's happening. So epsilon starting value, which will be, of course, 1.0. All right, and that will be our first epsilon value in the epsilon greedy strategy. But then we're going to let it decay, thanks to an epsilon decay value, meaning that we're going to reduce it little by little to test other epsilon values. All right, but we're going to do that up to a certain point, and that's why then the next hyperparameter variable I'm going to initialize here is going to be the epsilon, this time ending value, which will be the last epsilon value we want to test in our epsilon greedy strategy. And this value is actually going to be 0.01. Okay, so we start at 1, we end up at 0.01, and then by which decrement we're going to go from 1.0 to 0.01, well, that's going to be with, this time, the epsilon decay value, which according to you is going to be something like what? Well, we actually want to decay our epsilon starting value and then our next epsilon values by very little, by multiplying it by very close to 1 float, and that number is going to be 0.995. All right, so for example, the epsilon starting value is going to be 1, and then the next epsilon value after the first decay is going to be 1 multiplied by 0.995, meaning 0.995, okay? And then it's going to be 0.995 times 0.995, which is a little bit lower than 0.995. And we will do that until we reach 0.01, okay? So that will allow us to get different exploration in the epsilon greedy strategy. And then, final thing, what do we have to do? Well, of course, we have to create and initialize our epsilon variable, right? Because this is just a starting value, this is the ending value, so these are fixed. This is decay value, but then we want to have the epsilon value that will vary over the different decays. And so, how are we going to initialize this epsilon variable, of course? Well, with, of course, the epsilon starting value, which I copied before. All right? Perfect. And now we have one final training hyperparameter that we need to initialize, which are going to be the window of scores on 100 episodes. Okay, so again, in order to make things super clear, I'm going to call this variable scores on 100 episodes, which will contain that window of all the scores on the last 100 episodes. And how we're going to get that, how we're going to initialize this? Well, with a double-ended queue, in order to keep track, of the scores of the last 100 episodes. And how can we get that double-ended queue? Well, that's with a certain function called the decay function, inside which we will only enter this argument, maxlen, which will correspond, of course, to the 100 episodes. And that's it, my friends. We are now ready with the whole initialization of the training hyperparameters. So now we can finally move on to that next big step, very important step, the step where we finally make our AI intelligent. But of course, having the specific intelligence, not the general intelligence, to be able to land properly on the moon. So let's make that full loop happen in the next tutorial, and until then, enjoy AI.